There is a question that has quietly haunted the most rigorous minds in theoretical physics for decades, and it is not the kind of question you find plastered across the covers of sensational magazines. It is a question that emerges directly from the cold, unforgiving mathematics of general relativity. The question is this: if the universe is as vast and as old as the equations tell us it is, if stars like our sun have been burning for billions of years across hundreds of billions of galaxies, if the raw ingredients for complex chemistry are scattered across every corner of the observable cosmos, then where is everybody? Not as a poetic lament, not as a philosophical curiosity, but as a precise, quantifiable crisis in our understanding of the physical universe. Most people who confront this question immediately reach for a comforting answer. They suggest that perhaps advanced civilizations are out there watching, waiting, deliberately choosing to remain hidden. It sounds reasonable on the surface. A sufficiently advanced species might possess the technology to mask their electromagnetic signals, to encode their communications in formats we cannot detect, to observe from a careful distance without ever announcing their presence. And if you think about the universe purely in terms of light and radio waves, that hypothesis is difficult to dismiss. But here is where the elegance of general relativity intervenes with the force of mathematical law. Because the universe is not simply a dark room filled with invisible observers. The universe is a geometric structure. It is a four-dimensional fabric of space-time whose shape is determined not by choice or intent, but by the distribution of mass and energy within it. And mass and energy cannot hide. To understand why, you need to abandon the mental image of space as an empty void, a featureless black canvas stretching infinitely in all directions. That picture, intuitive as it feels, is fundamentally wrong. The picture that general relativity forces upon us is radically different. Imagine instead a vast, tightly stretched trampoline, and imagine that this trampoline extends in every direction as far as you can see. The surface is taut, smooth, and perfectly uniform. Now, place a heavy bowling ball near the center of that trampoline. Instantly, the fabric beneath it sags. It curves downward under the weight. The smooth geometry of the surface is deformed, warped into a distinctive well shape that radiates outward from the point of contact. Now, place a marble at the far edge of that trampoline and let it go. The marble does not travel in a straight line across the flat fabric. It curves, it bends toward the bowling ball. Not because some invisible hand is pulling it, but because the geometry of the surface itself has been altered. The marble is simply following the natural path through a curved landscape. This is precisely what Albert Einstein revealed to us in 1915 with the field equations of general relativity. Mass and energy do not simply sit inside space. They warp the geometry of space-time itself. Gravity is not a force in the Newtonian sense, a mysterious tug that reaches across empty distance. Gravity is the curvature of space-time produced by the presence of mass and energy. Every object in the universe, from the smallest asteroid to the most massive star, continuously deforms the space-time fabric around it. And crucially, this deformation is not something that can be turned off, muffled, or concealed. It is a direct, unavoidable consequence of having physical existence. Now bring this back to the question of hidden civilizations. The moment we entertain the hypothesis that an advanced species is observing us, we are forced to confront what that observation physically requires. Observation on an interstellar scale requires infrastructure. It requires energy collection on a massive scale. A civilization capable of monitoring a distant star system over geological timescales would need power sources that dwarf anything in our current technological imagination. The physicist Freeman Dyson described one such possibility decades ago, a structure now called a Dyson sphere, a megastructure built around a parent star to capture the totality of its radiant energy output. Even a partial Dyson swarm, a distributed network of solar collectors surrounding a star, would represent a concentration of engineered mass on an astronomical scale. And that concentration of mass, no matter how elegantly constructed, no matter how perfectly designed to absorb electromagnetic radiation rather than emit it, would still warp the local space-time fabric in a way that is physically distinct from a natural, unmodified stellar environment. This is the critical distinction. You can design a material that absorbs every photon that strikes it. You can engineer a civilization that produces zero radio frequency leakage. You can build a communications network that operates entirely in neutrino channels or gravitational wave modulations that our current instruments cannot decode. But you cannot engineer a material, a technology, or a physical process that prevents mass from curving spacetime. The deformation of spacetime geometry by mass is not a side effect of mass. It is what mass fundamentally is. In the language of general relativity, the stress-energy tensor, the mathematical object that encodes the distribution of mass, energy, momentum, and pressure throughout space, is the direct source term in Einstein's field equations. The curvature of spacetime is not caused by mass. It is mass expressing itself geometrically. To shield gravity would require you to erase the entry in the stress-energy tensor that corresponds to your civilization's physical existence. It would require you to subtract your mass from the universe's accounting ledger, and that is not technology. That is a violation of the foundational architecture of reality. Consider the implications of this for the trampoline. If an advanced civilization wished to remain hidden from us, they could, in principle, make themselves electromagnetically invisible. They could build their Dyson swarm from materials with perfect electromagnetic absorption coefficients. They could conduct all their affairs without a single photon escaping into the surrounding galaxy. If you were standing on one side of the trampoline in complete darkness, wearing clothes that absorbed all light, making no sound whatsoever, you might genuinely be invisible to the senses of any observer. But the moment you place your physical weight on the fabric deforms. Anyone else standing on that trampoline feels the surface beneath their feet tilt slightly toward your position. They feel the subtle change in the local slope of the surface, even if they cannot see you, hear you, or detect you in any other way. The geometry of the surface itself has betrayed your presence. Gravity is the universe's inescapable informant. Modern astrophysics has given us extraordinarily precise instruments for reading that geometry. The European Space Agency's Gaia mission has produced the most detailed three-dimensional map of the Milky Way galaxy ever assembled, cataloging the precise positions and kinematic motions of over 1 billion stars with an angular resolution that was unimaginable just decades ago. By tracking the precise velocities and trajectories of these stars across our galactic neighborhood, astrophysicists can reverse engineer the gravitational field responsible for those motions. They can construct a detailed map of where mass is concentrated in our galaxy, where the space-time fabric is sagging, where the gravitational wells are located, and how deep they run. This technique, known broadly as gravitational kinematics, treats the stars as test particles moving through the curved space-time geometry of the galaxy and uses their motions to reconstruct the underlying mass distribution that is producing that geometry. What does that map show us? It shows us a galaxy whose gravitational architecture is entirely consistent with dead baryonic matter, the ordinary atoms that make up stars, gas clouds, and dust, combined with the distributed, smooth halo of dark matter that envelops the galactic disk. There are no anomalous gravitational wells in our stellar neighborhood that cannot be accounted for by known natural processes. There are no regions where the kinematic behavior of stars deviates from what the equations predict for a galaxy populated entirely by natural, uninhabited astronomical objects. The geometric fabric of our local spacetime is pristine. It bears none of the signatures that a civilization of sufficient scale to monitor us would inevitably imprint upon it. To appreciate how sensitive this test truly is, consider what it would take to hide from it. A civilization operating a Dyson sphere around a star even 100 light-years from us would be concentrating stellar mass equivalent material into a relatively compact orbital shell. The gravitational signature of that structure would differ from an unmodified stellar system in ways that are, in principle, detectable through precise astrometric measurements of nearby stellar motions. The deformation in the spacetime metric produced by that additional engineered mass would propagate outward as a persistent, steady-state gravitational field, bending the trajectories of passing light and nudging the orbits of neighboring stars in ways that precise kinematic surveys could detect over time. This is not a speculative instrument sensitivity. The physics is clear. The deformation is there in the equations, and the equations are not negotiable. There is another channel through which the geometric betrayal of mass becomes detectable, and it is one of the most remarkable discoveries in the history of science. In September of 2015, the Laser Interferometer Gravitational Wave Observatory detected, for the first time in human history, a ripple in the fabric of space-time itself, a gravitational wave generated by the merger of two black holes over 1 billion light-years away. The stretching and squeezing of space-time by that event, though it amounted to a displacement smaller than 1,000th the diameter of a proton at the detector, was measurable. General relativity predicts that any accelerating mass, any object undergoing a change in momentum, radiates gravitational waves. The amplitude of those waves depends on the mass involved and the violence of the acceleration, but the principle is absolute. Accelerating mass curves space-time dynamically, and those dynamic curvature fluctuations propagate outward at the speed of light as gravitational radiation. Now consider the operational dynamics of a civilization engaged in interstellar observation. Their spacecraft must accelerate. Their megastructures, if they orbit their parent star, undergo continuous centripetal acceleration. Their energy collection infrastructure, whether orbital or otherwise, involves enormous masses in constant motion. All of this generates gravitational wave emission. The waves produced by individual technological components would be fantastically small, far below the sensitivity of current detectors, but the principle is physically unambiguous. A civilization of Kardashev Type 2 or Type 3 scale, operating across stellar or galactic distances, would be a source of gravitational wave emission that is, at least in principle, distinguishable from the natural astrophysical background. This brings us to an emerging frontier in gravitational wave astronomy known as the stochastic gravitational wave background. The universe is permeated by a faint, omnipresent hum of gravitational waves generated by the superposition of countless individual sources spread across cosmic history. Binary pulsars, in spiraling toward merger, massive black holes at galactic centers in their long orbital dances, the relic gravitational radiation from the violent epoch of cosmic inflation itself. These sources combine to produce a background gravitational wave signal that carries a specific statistical character, a spectral fingerprint that reflects the known population of natural astrophysical sources and the history of the universe's expansion. Pulsar timing arrays around the world, networks of millisecond pulsars used as precise cosmic clocks, are currently measuring this background with extraordinary precision. If a significant population of advanced civilizations were operating across our galaxy, their combined gravitational wave output from relativistic spacecraft, orbital megastructures, and large-scale mass movements would, in principle, contribute to that background. The spectral shape of that contribution would differ from the natural astrophysical background in subtle but potentially distinguishable ways, particularly at the frequencies corresponding to the orbital dynamics of planetary scale engineered structures. The current measurements of the stochastic gravitational wave background, while still accumulating sensitivity, are not revealing any excess power at the frequencies where technological civilization activity would be expected to contribute. The background is consistent within current uncertainties with purely natural astrophysical sources. We should also spend a moment on a concept called gravitational lensing because it illustrates with particular visual clarity just how transparent the universe is to gravitational probing. When a massive object sits between us and a distant light source, the curved spacetime around that massive object bends the path of the light, producing distorted, magnified, or even multiply-imaged versions of the background source. This is not a subtle effect. The Hubble Space Telescope has produced stunning images of distant galaxies warped into arcs and rings by the gravitational lensing of foreground galaxy clusters. But gravitational lensing works for any intervening mass, not just galaxies. A sufficiently massive artificial megastructure positioned along our line of sight to a distant star would produce a gravitational lensing signature detectable in the precise photometry of that star. Wide-field photometric surveys, monitoring millions of stars simultaneously for the telltale signatures of transiting objects would, in principle, catch such a signature. The large-scale photometric surveys we have deployed are not finding anomalous lensing events inconsistent with the known natural population of compact objects. The gravitational fabric between us and the distant stars is clean. What all of this converges on is a conclusion that is simultaneously simple and profound. The universe does not permit physical existence without geometric consequence. Every concentration of mass, whether it assembled itself through the blind processes of gravitational collapse and nuclear fusion, or whether it was carefully engineered by minds of extraordinary capability, writes its signature into the curvature of the space-time fabric. That signature is not optional. It is not a design flaw that can be engineered away. It is the universe's own method of bookkeeping. Mass tells space-time how to curve, and space-time tells us where the mass is. The relationship is symmetric and inescapable. The measurements we have assembled across decades of astrophysical observation, the kinematic maps of stellar motions in our galactic neighborhood, the gravitational wave background measurements from pulsar timing arrays, the gravitational lensing surveys of the surrounding cosmos, all of them converge on the same reading of the space-time ledger. Our corner of the galaxy is populated by natural astrophysical objects moving under the influence of natural gravitational fields produced by known matter distributions. There are no anomalous wells, no engineered deformations, no artificial gravitational signatures buried in the geometry of our local cosmic neighborhood. The universe, it turns out, is not a room full of hidden watchers who have mastered the art of concealment. It is a geometric structure that records the presence of every massive object without exception or mercy. If a civilization of sufficient scale to observe us existed nearby, the space-time fabric itself would betray them. The mathematics of general relativity would expose them as surely as a bowling ball exposes itself on a trampoline. The fact that we measure smooth, natural, predictable curvature in the geometry around us is not merely an absence of signal, it is a positive detection. A measurement of emptiness as precise and as rigorous as any measurement of presence. The geometry tells us that nobody is standing on our section of the trampoline, not because they chose to leave, not because they are hiding in the shadows beyond our electromagnetic sight, but because the fabric of reality itself has been examined, and the mathematics, cold and indifferent and absolute, shows no sign of them at all.